The largest structures in the universe, they all come from the same place. They started from the smallest things possible, a kind of microscopic foam, an energy that was everywhere in space. That's the story of quantum fluctuations, just tiny whispers in reality, but they grew. They ended up sculpting the galaxies, the whole cosmic web. So there's this link, this profound link between the quantum realm and the architecture of everything. It's like a hidden blueprint for the cosmos, and the question is, how did that random subatomic jitter decide where galaxies would form? What does that ancient code say about our place in the stars? What does it mean that our universe, that everything, is built on a foundation of quantum chance? That quantum foam, that sea of potential, is where it all starts. To get how a galaxy cluster a billion light-years across came to be, you have to look at the fabric of reality itself, a perfect, empty void. In classical physics, that's nothing. But the universe doesn't work that way at its most fundamental level. A perfect vacuum, a state of zero energy, is impossible. There's always a simmering activity, a restless energy. That's the heart of the uncertainty principle. For a vanishingly brief moment, energy can appear, borrowed from the universe, so long as it disappears again almost immediately. This isn't about what might happen. This is what does happen everywhere, all the time. Particles and their antiparticles flicker into existence, dance for an instant, and then annihilate each other, returning the energy. The vacuum of space isn't empty. It's a churning sea of these fleeting events. Physicist John Wheeler gave this a name, spacetime foam. At scales a trillion times smaller than an atom, the smooth fabric of space and time is thought to be frothy, turbulent, bubbling with these quantum fluctuations. And here's the crucial leap. In the first fraction of a second after the Big Bang, the entire observable universe was compressed into a volume smaller than a single atom. At that scale, these fluctuations weren't background noise. They were the only structures that existed. Tiny, random differences in energy density, hills and valleys in the fabric of the newborn cosmos. They were the primordial seeds. Then inflation happened. That period of rapid expansion did something. It took those quantum whispers, those subatomic hills and valleys, and stretched them across the entire sky. It magnified them from the quantum realm to the cosmic scale, freezing them into the geometry of the universe. So when we look at the map of the cosmic microwave background, that ancient afterglow, we're not just seeing heat. We're seeing a snapshot of those quantum fluctuations writ large. The hot spots, the cold spots, those variations are the direct, stretched-out imprint of spacetime foam. The universe's original blueprint, drawn in quantum ink, and from that blueprint, everything else followed. Gravity got to work, pulling matter toward those slightly denser regions, beginning a construction project that would last for billions of years. That blueprint was stamped onto the universe when it was at its most extreme. To see how those quantum whispers turned into cosmic commands, you have to look at the early cosmos. It was a realm of pure energy, a searing, brilliant plasma, so hot and dense that matter and space were still being forged. In the very first moments, everything we know, every galaxy, every star, every atom, was compressed into a volume smaller than a single proton. This wasn't a calm place, it was a violent, churning sea. Fundamental particles, photons, forces, all trapped in a frantic dance. In that primordial soup, the four forces we know: gravity, electromagnetism, the strong and weak nuclear forces, they were likely merged. A single, unified superforce, a state of near-perfect symmetry, a simplicity that's almost impossible to picture. But within that uniformity, the only variation came from the quantum fluctuations. Tiny, random differences in energy density, like the faintest ripples on the surface of a raging ocean, and then something monumental happened: inflation. This wasn't just expansion, it was exponential runaway growth, in a span of time so brief it defies analogy, a fraction of a second with more zeros after the decimal than we can write the universe ballooned. By a factor of at least 10 to the 26th power. It's as if a single atom swelled to become larger than our entire observable universe today. That incredible event did two critical things to those quantum ripples. First, it stretched them. Those microscopic hills and valleys in the energy field were magnified to astronomical scales, frozen into the geometry of spacetime as it expanded faster than light. Second, it made them permanent. Before inflation, these fluctuations might have just smoothed out, cancelling each other in the chaotic broth. But inflation pulled them apart so rapidly they could no longer communicate. No longer interact to erase each other. They were locked in, imprinted onto the cosmos like a signature pressed into cooling wax. The hot, dense plasma of particles now carried this imprint. This pattern of slightly denser and slightly less dense regions, gravity waiting in the wings, now had a script to follow. The stage was set. The microscopic had just been handed the keys to the macroscopic. And the construction of the cosmic web was about to begin. Gravity had its plan, but first, the universe needed a way to make that plan heard. That was inflation. A radical idea. It changed how we see the beginning of everything. You picture the early universe not as an explosion, but as a phase change, like water turning to ice. The fabric of reality shifted suddenly. This is cosmic inflation. The physicist Alan Guth pioneered it. The theory says in the first instant after the Big Bang, the universe was in a state of false vacuum energy. A latent power in empty space itself, and this energy had a peculiar property. It made space expand, not steadily, exponentially, unimaginably fast. For that brief moment, the universe expanded faster than light. Now, nothing can move through space faster than light, but space itself, the stage, has no such limit. It can stretch as fast as physics allows, and during inflation, it did. A region smaller than a proton was stretched instantly to a size larger than everything we can see today. Everything our telescopes see came from a speck smaller than an atom. This hyper-expansion did something critical to those quantum whispers. It amplified them. The fluctuations in the inflatoned field, that's the field driving the expansion. They weren't created by inflation. They were already there, the natural jitter of the quantum world. But as space stretched, those fluctuations stretched with it. A tiny hill in the energy field, a spot of slightly higher density, was pulled across light years. A microscopic valley became a vast cosmic trough. The random quantum noise was frozen into the geometry of the universe, magnified from the subatomic to the astronomical. Inflation turned faint static into a clear signal. It turned probabilistic quantum variations into definite classical differences, differences in density. Variations writ large across the cosmos. This was the moment the blueprint was set in space-time. The microscopic randomness of the quantum foam became the macroscopic architecture for everything to come. Without this amplification, those initial ripples might have stayed tiny. They might have smoothed away. Inflation gave them permanence and scale. It took the signature of the quantum world and signed it across the entire sky. A signature gravity would spend 14 billion years following. The universe had this pattern now imprinted on it, and it was ready for the next part. You know, picture a tiny wrinkle on a deflated balloon, just a faint crease, but then you inflate the balloon. You do it fast with one big breath, and that small wrinkle gets stretched. It grows. It becomes this huge, continent-sized feature across the balloon's surface. That's what inflation did to those quantum ripples. It was the ultimate stretch. The wavelength of each fluctuation, once smaller than a subatomic particle, got pulled across distances we now measure in billions of light years. What had been random, tiny variations in the energy field, they were transformed. They became the first large-scale imperfections in a universe that was trying to be uniform, regions of space that were slightly denser, right next to regions that were slightly less dense. The differences were incredibly subtle. We're talking about variations in density of just 1 part in 100,000. If the early universe were a perfectly smooth ocean, these were the gentlest swells. Hills and valleys in the fabric of reality, so faint you'd almost miss them, but they were everything. They were the seeds, and they carried a specific mathematical signature. A pattern that inflation predicted, a nearly scale-invariant spectrum. That means the fluctuations, when stretched, looked statistically similar no matter what scale you looked at. Whether you examined a patch of sky the size of a galaxy or the size of a supercluster, the pattern of hills and valleys was proportionally the same. This signature is a direct prediction of the inflationary model. It's a fossil, a piece of evidence frozen in time, and this is what our most powerful telescopes, like the Planck satellite, have been searching for in the cosmic microwave background. They aren't just mapping heat, they're forensic scientists looking for that specific fingerprint left by the universe's most violent growth spurt. They're reading the ancient code written by quantum chance and cosmic expansion. And from this coded map, the force that would build the cosmos was about to awaken. That fingerprint is the primordial power spectrum. It's like a cosmic barcode, a graph of the universe's original sound. One axis is the physical size of a fluctuation. The other is its strength, its amplitude. This graph tells you how much the density of the universe varied. Whether you were looking at a region the size of a city or the size of a continent, and inflation predicted this graph would have a very specific shape. It should be nearly scale-invariant. That's a technical term. It means the strength of those density variations was roughly the same, whether the fluctuation was originally small, medium, or large. The quantum jitter that created a hill the size of a planet also created, with equal probability, a hill the size of a galaxy cluster, and when inflation stretched them, it preserved that relationship. That's why the cosmic web has structure on every scale we look, from dwarf galaxies to the vast, empty voids between superclusters. The blueprint wasn't drawn for one specific size. It was a universal pattern, but it gets more interesting. The prediction isn't for a perfectly flat line on that graph. There should be a slight tilt. A gentle slope. The fluctuations on the very largest scales should be ever so slightly stronger than those on smaller scales. That tiny deviation is a gold mine. That tilt isn't a mistake, it's a message. It encodes details about the inflattened field itself, how its energy changed during that explosive moment. Was the expansion slowing down as it ended? How steep was the slope of that energy landscape? The precise value of this spectral tilt helps rule out entire families of inflationary models. It's how we test the physics of the universe's first fraction of a second. So when we look at a map of the cosmic microwave background, we're not just seeing a baby picture, we're holding a detailed technical schematic. A schematic drawn by quantum mechanics, signed by inflation, and delivered to gravity. Every cluster of galaxies, every filament of the cosmic web, traces back to a specific point on that primordial graph. Our local neighborhood, the Milky Way and Andromeda in their slow gravitational waltz, exists because of a particular quantum fluctuation. One that happened to have the right amplitude and the right scale. We are here because of a line on a graph that describes the universe's first whisper. That ancient barcode is still visible, we can see it. It's the oldest light in the universe. About 380,000 years after the Big Bang, something happened. The universe had been expanding and cooling from that initial heat, and it finally reached a temperature cool enough for atoms to form. For the first time, protons could capture electrons. They created neutral hydrogen. Before that moment, the cosmos was an opaque fog, a thick plasma. Light particles, photons, were constantly scattering off free electrons. They couldn't travel straight. It was like a dense, glowing mist, but when atoms formed, the electrons were bound, the fog lifted, the universe became transparent. And the photons flying around at that instant were set free. They've been traveling unimpeded for over 13 billion years. We see that light today, stretched and cooled by expansion, as the cosmic microwave background. A faint, cold glow that fills every direction, a snapshot of the universe at its first clarity, a baby picture taken when the cosmos was just a fraction of its current age. And this picture is not blank. When satellites like COBE and WMAP and Planck mapped this glow, they found it wasn't perfectly smooth. It's mottled, a tapestry of subtle hot and cold spots. Temperature variations of just a few millionths of a degree. These anisotropies, these tiny imperfections, are the direct descendants of those quantum fluctuations. They mark the spots where, 380,000 years after the Big Bang, the plasma was slightly denser or slightly less dense. In the denser regions, photons had to climb out of a slightly deeper gravitational well. They lost a tiny bit of energy, so they appear slightly cooler to us. In the less dense regions, the opposite occurred. The pattern we see in the CMB is a precise map. A map of the density blueprint that inflation created and stamped across the cosmos. So when you look at an image of the cosmic microwave background, those colorful splotches aren't artistic. They are the literal seeds of destiny. Every bright spot, every dark patch corresponds to a region where gravity would soon get to work. That slightly hotter, denser spot over there. That's the progenitor of a massive supercluster of galaxies. That fainter, cooler region that will become one of the great cosmic voids. The entire future large-scale structure of the universe is encoded in that image. It's all there in its infancy, a frozen moment before the first star ever ignited. It shows us the raw material, the material from which everything, including our own galaxy, would eventually coalesce. This is the observational proof that our cosmic story began in quantum chaos. The patterns in that ancient light are a language. We just had to learn to read it. When the first detailed maps came in from satellites like Planck, cosmologists saw more than splotches. They saw a kind of order inside the randomness. To understand it, you don't just look at the spots, you measure the relationships between them. How likely is a hot spot of one size to be next to a cold spot of another size? They plot that on a graph, the angular power spectrum. It sounds complex, but the idea is simple. It's like listening to the sound of the early universe. If you could hear the cosmic microwave background, it wouldn't be a single tone. It would be a chord, a rich note made of many frequencies, all playing together. The angular power spectrum is the sheet music for that chord. It tells you the volume of each harmonic. The smaller spots on the map, those are higher-pitched notes. The larger features, the continent-sized ones, those are the deep bass notes of the cosmos. And the shape of this spectrum, the way the volume rises and falls across the notes, that's a direct prediction of inflation. When they plotted the data, the match was stunning. The observed spectrum lined up almost perfectly with the prediction, if the seeds were quantum fluctuations stretched by inflation. The most prominent peak on that graph, the loudest note in the chord, that corresponds to the most common size for those primordial variations. It tells us the preferred scale where gravity first began to pull matter together. But the harmony doesn't stop there. The relative heights of the second and third peaks, they're exquisitely sensitive probes. They reveal the total density of ordinary matter in the early universe. They tell us about the pressure of the photon baryon fluid, that searing plasma. It acted like a spring, causing matter to oscillate in and out of the dense regions. We're measuring the echoes of sound waves that traveled through the infant cosmos, frozen when the light was set free. Every wiggle on that power spectrum graph is a piece of the puzzle. Together, they confirm a universe that is geometrically flat, a specific mix of dark matter, ordinary matter, and dark energy. They tell us the universe is 13.8 billion years old. And most profoundly, they tell us the blueprint for all of this, for the entire cosmic web, was drawn by quantum mechanics. Those microkelvin variations in temperature, those faint whispers of heat and cold, they're the amplified classical signatures of subatomic uncertainty. They are the proof the largest structures we see were born from the smallest things possible. Gravity, that force we feel holding us down, it became the builder. Sir Isaac Newton gave us the law. Every bit of matter attracts every other bit. The pull depends on mass and on distance. Later, Albert Einstein refined it. He showed gravity as the curvature of spacetime, shaped by mass and energy. But the principle stayed the same, and it was about to build things, those regions of slightly higher density from the quantum fluctuations. They were the key. They had a little more mass, so they exerted a slightly stronger pull, an almost imperceptible advantage, a whisper of a tug, but over time that whisper became a command. Matter began to respond, both ordinary matter and dark matter. It started to drift slowly toward those overdense seeds. This is gravitational instability. A stable, uniform universe would have stayed a soup, but ours wasn't uniform. It had those tiny imperfections, and in a universe with gravity, an imperfection isn't a flaw. It's an opportunity, it's a starting point. The slightly denser region pulls in a little more matter. As it gains mass, its pull grows stronger. That stronger pull attracts even more matter from a wider area. It's a feedback loop, a snowball effect on a cosmic scale. What began as a 1 part in 100,000 variation became magnified, enhanced by gravity's patient work. Over hundreds of millions of years, this gathering accelerated. The diffuse clouds, the primordial gas and dark matter began to coalesce. The subtle hills in the density landscape grew into mountains. The valleys sank deeper, becoming the vast, empty voids between galaxies. Gravity was taking the faint pencil sketch and inking it in with bold, three-dimensional strokes. It was setting the stage for collapse, for the first stars to ignite, for the first galaxies to gather. The universe was no longer a smooth, expanding broth. It was becoming a web, threads of matter drawing together under the silent, unwavering law of attraction. Ordinary matter had a problem. It was under intense pressure. In that early plasma, photons, particles of light, were constantly hitting protons and electrons. That created a powerful outward force, a kind of cosmic wind. And it was pushing against gravity's pull. It kept ordinary matter stirred up, baryonic matter, like trying to gather leaves in a hurricane. Gravity's whisper was being shouted down by the chaos of light. The math was clear. If atoms were the only thing, the universe would have taken much, much longer to clump, to form galaxies. The cosmic web we see today wouldn't have had time. Something else was working, a hidden player, providing extra gravitational glue to speed up the whole construction. That player is dark matter, a mysterious substance. It doesn't give off light. It outweighs ordinary atoms by about 5-to-1. We can't see it directly. It doesn't emit or absorb or reflect light. It passes through ordinary matter like a ghost. But we know it's there from its gravity. It bends light from distant galaxies. It sets the rotation speeds of stars inside galaxies. And in the early universe, it had a key advantage. It was unaffected by that radiation pressure. While photons battered ordinary atoms, they just streamed right through dark matter. That gave dark matter a huge head start. Freed from the electromagnetic storm, it could respond only to gravity. Those quantum fluctuations, those seeds of density, were its blueprint. Dark matter began to clump first. Under its own silent attraction, it came together into vast, diffuse clouds, immense halos stretching across hundreds of thousands of light years. These dark matter halos weren't structures like galaxies. They were gravitational scaffolds, deep, invisible wells of potential. And once these wells were there, they changed everything for ordinary matter. As the universe kept expanding and cooling, the radiation pressure finally eased. The cosmic hurricane died down. The ordinary atoms, the hydrogen and helium gas, were now free to fall, and they fell into the waiting gravitational pull of the dark matter halos. The quantum blueprint got executed twice, first in dark matter, which built the underlying framework, then in visible matter, which flowed into that framework to light it up with stars. So when we look at a spiral galaxy like our Milky Way, we're only seeing the luminous tip of a vast dark iceberg. The stars and gas we see are tracing the shape of something much larger. And entirely unseen, they're following the contours of a dark matter halo, one that formed over 13 billion years ago from a quantum whisper in the first instant of time. The universe was building a skeleton, this framework of dark matter. It traced the lines of that original blueprint, forming a cosmic web, filaments and huge, empty voids. Where those dark threads crossed, where gravity pulled the hardest, matter gathered. It made dense knots. These were the first dark matter halos, not galaxies yet. They were the gravitational wells, the deep pits where galaxies would form. And into these wells, the ordinary stuff began to flow. Hydrogen and helium gas, the elements from the Big Bang, streaming along the dark filaments. Pulled by the tug of the unseen mass, as this gas fell into the halos, it was moving fast, colliding, compressing, and in that chaos it started to shed energy. To cool, that cooling was everything. Hot gas has too much energy to clump. It bounces and swirls, but as it radiates heat away, it can slow down, it can condense. So, inside these massive dark halos, the gas cooled and condensed into swirling, dense clouds, the first proto-galaxies, the luminous seeds of today's galaxies. They weren't grand spirals, they were small, chaotic, and ferociously bright with the first massive stars. This building process worked from the ground up. Small dark matter halos formed first, then, drawn together by gravity, they merged. They crashed into each other, building larger structures. A small halo would merge with another, and that combined halo would attract more. It was a cosmic assembly line, a hierarchy of growth, and the guiding pattern for all of it, the map for where mergers happened and how large things would get, was that initial pattern of density fluctuations. The subtle hills and valleys frozen into the cosmos by inflation. That quantum jitter from the first instant had, billions of years later, decided where the first lights would switch on. Where the darkness would first be broken by a newborn sun. Those first stars left an echo, a cosmic echo we can still measure. It's in the positions of galaxies. That's baryonic acoustic oscillations. You have to go back to the plasma before the cosmic microwave background. Photons and ordinary matter, the baryons, were locked together. A single hot fluid, gravity was pulling matter into those overdense seeds, but there was a counterforce, radiation pressure from the photons, pushing outward. So you had a tug of war, gravity pulling in, radiation pushing out, that created an oscillation. A sound wave moving through the early cosmos, like dropping a stone in a pond. A ripple expands in a circle. In the early universe, an overdense region was that stone. A spherical shell of compressed matter and radiation expanded outward. A pressure wave, but this wasn't water. It was the whole observable universe, and the wave moved at a huge fraction of light speed. This went on for nearly 400,000 years. Until recombination, when atoms formed and the photons decoupled, the music stopped, the sound waves froze, the outward moving shells of matter, now without photon pressure, just stopped. They were left as subtle, spherical overdensities, all at the same distance from their original seeds. That distance is the sound horizon, a fixed scale. A standard ruler imprinted on the cosmos, about 490 million light-years in today's universe. And this is what's fascinating now. When we map millions of galaxies in 3D, it's not just random. There's a subtle statistical preference. Galaxies are slightly more likely to be separated by that specific scale, the size of the frozen sound wave, than by any other distance. It's like every galaxy cluster has a faint, ghostly shell around it, a shell where other galaxies are a little more likely to be. That preferred separation is the Baryonic acoustic oscillation. A fossilized sound wave, a whisper from the universe's fiery infancy, now encoded in the large-scale structure. And because we know the physical size of that original sound horizon from early universe physics, it becomes a cosmic measuring tape. By seeing how that apparent scale looks at different distances and so different times, we can measure how the universe has expanded over billions of years. It gives independent, powerful confirmation of dark energy and the accelerating expansion, another line of evidence written not in light but in the architecture of the cosmic web. All tracing back to those initial quantum seeds and the physics of the primordial plasma. The frozen sound waves and the dark scaffolding, they all led to this. A structure so vast it just defies intuition. 13.8 billion years of gravity doing its work. The universe has woven itself into a cosmic web. A network of breathtaking scale and delicate intricacy. If you could step back far enough to see billions of light years at a glance, you wouldn't see a uniform scatter of galaxies. You'd see architecture, great luminous threads of galaxies stretching across the emptiness, like strands of a spider's web, and at the intersections of these filaments you find dense knots. Massive clusters, thousands of galaxies bound together by gravity, and between the threads, between the clusters, lie the voids, immense, nearly empty regions of space. Spheres of darkness that can span hundreds of millions of light years. This is the large-scale structure. It resembles a sponge or the froth on a cosmic sea. It's the universe's skeleton made visible by the light of its cities, and we know this because we've mapped it. Projects like the Sloan Digital Sky Survey. They've catalogued the positions of millions of galaxies, created three-dimensional atlases of the cosmos, and when you plot those positions, the pattern emerges from the data. Not as a picture, but as a statistical reality. The galaxies aren't placed at random. They trace out the filaments and the walls. They outline the voids. They huddle in the clusters. This is the ultimate outcome of that ancient process. The quantum seeds stretched by inflation, grown by gravity, and given form by dark matter. And here's the profound confirmation. The statistical pattern of this web, the specific way galaxies are clustered together at different scales, it matches a prediction. The prediction from that primordial power spectrum, the barcode born from quantum fluctuations. You can take the distribution of galaxy clusters today and run it backward through the equations of gravitational growth. And it leads you right back to those tiny 1 part in 100,000 variations in the early universe. So the cosmic web isn't just a structure. It's a fossil of quantum mechanics magnified to the scale of the observable cosmos. The same physics that governs electrons in an atom also dictated where the great walls of galaxies would form. It means the universe has a memory, a deep structural memory of its first instant. When we look out at the vast dark voids and the brilliant filaments of galaxies, we're looking at the ghost of quantum uncertainty. Written in stars, the cosmic web is a fossil, but proving that means running the experiment backward. You build a new universe from scratch inside a supercomputer. That's the world of numerical simulations. Cosmologists don't just observe, they recreate, and they start with the only ingredient that matters, those initial conditions. The primordial power spectrum from the quantum fluctuations. They take that mathematical blueprint, the barcode of the early universe, and translate it into a starting grid. A three-dimensional box, a vast chunk of space. They fill it with millions, sometimes billions, of virtual particles. These aren't atoms, they're tracers. Stand-ins for the dark matter, the cosmic scaffolding. Each particle carries a tiny bit of mass. Their initial positions aren't random. They're placed to reflect that exact pattern of density variations. The subtle hills and valleys from the cosmic microwave background, encoded right into the starting code. Then you press play, you let the simulation run. The only rule is gravity, the simple, unyielding law of attraction. Every particle pulls on every other particle. Over billions of years of simulated time, the computer calculates the dance. The particles begin to move, slowly at first, drifting toward the overdense regions, and the feedback loop begins. Gravity amplifies the tiny differences. The virtual dark matter starts to clump, to merge, to form halos. As the simulation unfolds, something happens on the screen. A structure emerges, not by design but by pure physics. Filaments of particles stretch across the virtual void. Where they intersect, dense knots form, and between them, vast empty regions open up. It looks unmistakably like the cosmic web. This is what happened with projects like the Millennium simulation. Starting from those quantum-informed initial conditions, it produced a virtual universe. And when you compare its statistical properties to our own, it's a near-perfect match. The distribution of clusters, the sizes of the voids, the thickness of the filaments. They all line up. These simulations are more than pretty pictures. They're rigorous tests. If you start with the wrong initial conditions, if the primordial fluctuations were too strong or had the wrong pattern, the resulting cosmic web looks nothing like what we observe. The fact that our best simulations, when fed the quantum blueprint, reproduce the universe we see, that's some of the strongest evidence we have. It tells us the story is coherent. That the journey from quantum jitter to galactic supercluster isn't just a beautiful idea. It's a demonstrable computational fact. The universe in its deepest architecture is a prediction that came true. But which inflation model is correct? That's the next question. Cosmic inflation is a framework, a beautiful idea, but it's not one specific story. It's a family of possible stories. Different models propose different kinds of inflaton fields, that hypothetical energy that drove the expansion, and each model makes slightly different predictions. It all comes down to the details of the quantum fluctuations. Their precise statistical properties become a fingerprint, identifying which inflationary scenario actually happened. You have a crime scene, the cosmic microwave background. The pattern of hot and cold spots is the evidence. Inflation is the general motive, the how of the expansion. But to identify the specific culprit, the exact physics, you need finer clues in that evidence. Different models leave different subtle marks on the fluctuations. Some models predict the fluctuations were perfectly scale-invariant. Others predict that very slight tilt where the strength of the fluctuations depends on their size. The exact value of that spectral tilt, measured by missions like Planck, helps rule out entire classes of theories. But there's an even more sought-after clue, a potential smoking gun. Some models predict the violent stretching of spacetime would have generated ripples, primordial gravitational waves. These aren't waves in water or air. They are literal ripples in spacetime, stretching and squeezing distances as they pass. And if they were produced during inflation, they would have left a unique, curling pattern in the polarization of the cosmic microwave background. Scientists call this B-mode polarization. The hunt for this signature is one of the most intense pursuits in cosmology. Telescopes are built at the South Pole, on mountain peaks, launched on balloons, all trying to detect this faint, swirling pattern in the ancient light. Finding it would be a direct window into the energy scale of inflation. It would tell us how powerful that event was. It would confirm a major prediction and point toward a subset of models. So the quantum fluctuations are more than just seeds. They are a detailed diagnostic report from the universe's first moment. By measuring their properties, their strength, their scale dependence, the possible imprint of gravitational waves, we are doing forensic cosmology. Using the largest structures as evidence to investigate the smallest scales and the highest energies, the blueprint doesn't just show us what was built. It tells us about the tools and the forces that did the building. Every subtle characteristic we measure in the cosmic web is a message, helping us narrow down the exact story of how everything began. The standard model of cosmology, built on inflation and quantum seeds, it's a triumph. It explains an astonishing range of what we see, but our maps are more precise now. And a few strange features have emerged in the data, anomalies. They don't quite fit the simplest story. They're not contradictions, not yet. They're more like faint whispers from the edge of our understanding. Hints that the blueprint might have lines we haven't learned to read. One of the most famous is the cold spot in the cosmic microwave background, a region in the constellation Eridanus that's significantly colder than the model predicts. A large, puzzling patch of chill. Statistically, it's unusual. It could be a rare fluctuation, a cosmic coincidence, but its size and significance have led to other ideas. More exotic ideas. Could it be a shadow, the imprint of a collision with another universe during inflation, or perhaps a sign of an immense void, an underdense region so vast it leaves a cold imprint on the ancient light? These are speculative, but they show how a single anomaly can open doors to profound questions. Then there are the alignments. When scientists study the largest structures, like the clustering of quasars across billions of light years, some analyses suggest unexpected correlations. Patterns that stretch across distances so vast they shouldn't be able to communicate. According to standard cosmology, some call this the axis of evil, a playful name for a potential directional preference in the universe. One that challenges the assumption of perfect uniformity. What could cause that? A relic of the pre-inflationary universe, a scar from a time before the rapid expansion smoothed everything out. Or a more complex form of inflation, multiple fields, a different geometry. These puzzles are not failures of the theory, they are its growing pains. They remind us that every great scientific narrative is provisional, a map that gets more detailed with each new survey. The fact we can measure the cosmos so precisely that we even notice these subtle deviations is a testament to how far we've come. They are opportunities. Each one is a question mark carved into the data, an invitation to probe deeper, to ask what physics, at energies far beyond our particle colliders, might have left its fingerprint on the quantum fluctuations themselves. The story of how the smallest things shaped the largest structures is not fully written. Its next chapters may be hidden in these anomalies, waiting for a sharper telescope. A more powerful simulation, a bolder idea to reveal their meaning. These anomalies might not just be quirks in the data, they could be cracks in the wall of our universe. Hints of something beyond it, and that leads to one of the most speculative extensions of inflation, the multiverse. This idea comes from the math of eternal inflation. If inflation is driven by a quantum field, then in some models it never truly stops everywhere. It ends here in our patch, creating our bubble of spacetime. But in other regions, the conditions stay right. Inflation continues eternally there, spawning new bubbles endlessly. Each bubble is a separate universe, pinched off from the others, with its own distinct properties. The physical constants we think of as fixed: the strength of gravity, the mass of an electron, they might be randomly determined in each bubble as it forms. In some, gravity could be so strong that stars burn out in 1 million years. In others, so weak that no stars ever ignite. Our observable cosmos, with its specific quantum blueprint and its life-friendly laws, becomes one possibility. In an infinite cosmic landscape, the fluctuations that seeded our galaxies weren't chosen. They were drawn from a cosmic lottery. It's a staggering shift. It suggests the ultimate origin of our cosmic architecture might not be a single deterministic event, but a random selection from a vast ensemble of possibilities. We find ourselves in a bubble where the quantum jitter had just the right amplitude, where dark matter clumped just so, allowing galaxies and stars and planets to form. It reframes our entire story. The search for a single, elegant theory of everything might need to accommodate this landscape of possibilities. While the multiverse is still speculative and currently untestable in the traditional sense, it emerges naturally from the leading theories of the very early universe. It pushes us to ask a deeper question. Are the laws of physics and the specific quantum seeds that built our world, are they necessary, or are they, in the grandest scheme, simply local and contingent? The answer, if there is one, lies not just in looking back at our origins, but in contemplating the nature of reality itself. The story isn't finished. It's being written right now. We have new eyes on the sky. Our maps of the cosmic web are about to become unimaginably detailed. The next generation of observatories on the ground and in space, they're designed to read that ancient quantum code with a precision we've never had before. They are the ultimate tests of our theory. The quest to understand those first whispers, it's pushing us to build the most sensitive instruments in history. On a high, dry plateau in Chile, the Simons Observatory is taking shape. It's an array of telescopes. Its primary purpose is to stare at the cosmic microwave background. With a resolution and sensitivity that dwarfs anything before, its cameras will measure the faint polarization of that ancient light, hunting for the swirling B-mode pattern, the telltale sign of primordial gravitational waves from inflation, finding that signal that would be a direct glimpse into the universe's most violent moment. It would tell us the energy scale of inflation itself, ruling out vast swaths of theoretical models, pointing toward the true physics of Genesis. But the cosmic blueprint isn't just in the ancient light. It's also in the modern structures, the structures that light built. To trace its full architecture, we need to map the cosmic web in 3 dimensions. Across billions of years, that's the mission of the Nancy Grace Roman Space Telescope, scheduled to launch later this decade. Roman will perform a gargantuan survey of the sky. It won't just take pictures, it will measure the precise positions and distances of hundreds of millions of galaxies. It will construct the most comprehensive 3D atlas of the universe ever made. With this map, scientists will measure the Baryonic acoustic oscillations, those frozen sound waves. They'll measure them with razor-sharp accuracy across cosmic time. They will trace the subtle growth of the cosmic web's filaments and clusters, testing our models of dark matter and dark energy against the raw data of reality. Meanwhile, the European Space Agency's Euclid mission is already at work. From its vantage point in space, Euclid is surveying billions of galaxies to study the dark universe. Its primary tool is weak gravitational lensing. By measuring how the shapes of distant galaxies are subtly distorted as their light passes through the cosmic web's dark matter scaffolding, Euclid will create a mass map of the invisible universe. This map will show us the dark matter skeleton in exquisite detail, allowing us to see if it aligns perfectly with the distribution of visible galaxies, and if its evolution matches predictions from those quantum initial conditions. Together, these missions form a new frontier. They will measure the statistical properties of galaxy clustering with such fidelity that we can search for deviations from the simplest inflationary predictions. They will refine the measurement of the spectral tilt, that subtle slope in the cosmic barcode. They will refine it to a razor's edge. They will either find the signature of primordial gravitational waves or push the limits of their absence, forcing theorists to refine their ideas. Every data point from these observatories is a vote on what happened in that first sliver of a second. The story that began with a quantum jitter is now being scrutinized by the very structures it created. We are using the grand cosmic web, the largest thing we can see, as a laboratory to probe the smallest scales and the highest energies. The universe left us a message in its architecture, and we are finally building the tools to read every single word. That ancient barcode is a message. It's more than a pattern. The quantum fluctuations that seeded everything, they carry information, a cosmic code. When cosmologists look at the map of the early universe, they're not just seeing splotches of heat. They're looking at a data stream broadcast from the moment of creation, and decoding it reveals the physics of that first instant. The information is stored in the statistics. In the fluctuations, are they perfectly random, like static, or is there a hidden order in the chaos? The simplest models say the fluctuations should be Gaussian. That's a statistical term. It means if you plot their strengths, they follow a bell curve. Most regions are near the average temperature, a few very hot or very cold spots at the extremes just by chance. Gaussian randomness is the fingerprint of a simple inflation, a quiet birth. But if we find deviations from that perfect bell curve, if we detect non-Gaussianity, that changes everything. It's a sign of more complex physics during inflation. Think of it like listening to the sound of the early universe. Gaussian noise is a steady hiss. Non-Gaussianity would be a faint crackle, a pop, a moment where the hiss changes tone. Those subtle signatures could mean the inflattened field interacted with other fields. Or that it had a more complicated shape, a landscape where it bumped and jostled as it rolled. It could even hint at other particles, born at those incredible energies that left a mark on the quantum seeds. Reading this code is cosmic archaeology. We're using the largest structures as a time machine to probe energies 1 trillion times higher than any particle collider we could build. The Large Hadron Collider smashes protons at phenomenal speeds, but the energy scales of inflation are so far beyond that, they're practically inaccessible. Except for one experiment, the universe ran it for us 14 billion years ago, and it recorded the results in the cosmic microwave background, in the large-scale structure we see today. By measuring the statistics of galaxy clusters, the subtle patterns in the ancient light, we're reading the lab notes from the highest energy physics experiment that ever was. Every subtle correlation, every tiny deviation from perfect Gaussian randomness, it's a clue about what the fabric of reality was like when everything began. The quantum code is a message. It comes from an energy frontier we can't reach. The amplitude of those fluctuations, their strength, it's not arbitrary. It's a measurement, a direct measurement of the energy scale where inflation happened, and the number is staggering. To produce the density variations we see, the seeds for all galaxies, inflation had to occur at an energy around 10 to the 16 gigaelectronvolts. That's a 1 with 16 zeros, a scale so immense it dwarfs our mightiest particle collider, the Large Hadron Collider, by a factor of 1 trillion. At that energy, the forces of nature begin to change. According to our best theories, electromagnetism, the weak and strong nuclear forces, they're not separate. They merge. They become one unified force. This is the grand unification scale, the energy where particle physics and cosmology collide. This link suggests the inflattened field, that entity that drove the expansion, wasn't just an abstract mathematical trick. It could be a real particle, a cousin to the Higgs boson maybe, or a field predicted by theories like supersymmetry, which says there's a partner for every known particle. The universe's first event, its most dramatic event, might have been triggered by a fundamental particle acting on spacetime itself. So when we study the patterns in the cosmic microwave background, we're not just doing astronomy. We're conducting particle physics, using the entire observable universe as our detector. The cosmic web is the readout from an experiment that ran once, at energies we could never recreate. Every filament, every void is a data point. This transforms the quest, searching for the signature of primordial gravitational waves, or for non-Gaussianity in the fluctuations. It's no longer just about confirming inflation. It's a search for clues about grand unification, about quantum gravity, about the nature of matter and energy at the birth of everything. The cosmos holds the answers to questions our machines are too small to ask. The code from the beginning forces a strange truth on us. Our cosmic home, the Milky Way, it's at this specific location because of a quantum roll of the dice. One particular fluctuation out of countless possibilities happened to be right here. The whole architecture of the cosmic web, the brilliant filaments and the dark voids, it's not a predetermined design. It's a single realization, one version pulled from a quantum probability distribution, a pattern that could have been different, and that introduces chance right into the foundation of everything. It means our universe's large-scale structure, it's not the only possible outcome. It's just the one that happened to unfold. We're living in the aftermath of a primordial lottery. That idea can feel unsettling. It seems to place our entire cosmic context on a foundation of randomness, but that's only one side of the story, because while the specific pattern was random, the rules of the game were not. The laws of physics provided the rigid framework. Quantum mechanics dictated that fluctuations had to exist. General relativity dictated how gravity would respond. Inflation provided the mechanism to stretch them and freeze them. These were the necessary constraints, the unbreakable laws that channeled that randomness into a coherent form. So the universe we see, it's not purely random chaos. It's randomness filtered through necessity, a dance between chance and law. So is our place in the cosmos a mere accident? Or is it an inevitable expression of deeper physical principles? Maybe the answer is in the combination. The specific address of our galaxy that might be accidental. A product of quantum chance, but the fact that galaxies could form at all, that stars could ignite and planets could coalesce, that seems to be written into the fabric of the laws themselves. The physics had to allow for complexity to emerge from simplicity. This interplay, it's the heart of our search for meaning now. It suggests that while our local neighborhood might be contingent, the potential for a rich, structured cosmos, even a life-bearing one, that may be a fundamental feature of reality. We are not the center of a planned creation, but we're not meaningless flotsam in a chaotic void either. We are participants in a grand, lawful process that began with a whisper of uncertainty. Our existence is a testament to the fertile ground that lies between absolute determinism and pure randomness. And it's in that fertile ground that stories, including our own, become possible. Picture a pot of popcorn kernels. Each one is sealed. Inside, there's a little bit of moisture. It's random. Some kernels have a tiny bit more water, some a tiny bit less. That's the fluctuation, the small, random difference. Then you apply heat. That's the inflation, a sudden, intense energy. The kernels don't just get warm. They expand violently. The water turns to steam, the pressure builds, and the shell breaks, but they don't all pop together. They don't all become the same size. The kernels with that slight extra moisture, that initial overdensity, they pop first. They expand the most. They become the biggest, fluffiest pieces. The ones with less moisture might pop later, or they stay smaller, denser. Now you look at the bowl. It's not a uniform foam. It has a structure, clusters of big, fluffy pieces stuck together. Smaller pieces in the gaps, and there are empty spaces, voids where no popcorn landed. The entire architecture of that bowl, which pieces are neighbors, where the clusters are, where the voids are, that was decided by those initial, invisible differences in moisture. That's the story. The kernels are regions of the early universe. The random moisture is the quantum fluctuation. The heat is the inflationary expansion. The final bowl, with its clusters and voids, is our cosmic web. The Milky Way and the local group. We're one particular fluffy cluster in that bowl. our specific location, which galaxies ended up near us, that was decided by a microscopic roll of the dice. Over 13 billion years ago, this makes the profound field tangible. A grand, universal structure emerges, not from a detailed plan, from simple rules acting on random, initial conditions. The universe didn't need a blueprint for each galaxy. It just needed a rule, gravity, and a seed of variation. The rest was a cosmic cascade, as inevitable as popcorn popping in a hot pan. The clock starts at a fraction of a second so small it's almost meaningless. 10 to the negative 36 seconds. That's when inflation begins. Space itself stretches exponentially. And those quantum fluctuations get stretched with it. They freeze into the fabric of reality. They become the first classical structures, subtle variations in density. The blueprint is drawn. The universe is less than a trillionth of a second old, and its entire future is already encoded. Then you fast forward. The universe expands and cools. For nearly 400,000 years, it's a hot, opaque plasma. Gravity is already at work, pulling matter toward those overdense seeds, but light is trapped. It bounces endlessly. Then, at the 380,000-year mark, the temperature drops enough for atoms to form. The fog clears. The cosmic microwave background is released. It carries a snapshot of those seeds. The hot and cold spots we see in that ancient light, they're not galaxies. They're the raw potential. The map becomes visible. Now the dark ages begin. For millions of years, the universe is dark. No stars, no galaxies, just vast clouds of neutral hydrogen and helium gas, and the invisible scaffolding of dark matter. Gravity keeps pulling patiently. Within the dark matter halos, the gas begins to cool. It condenses. Around 200 million years after the Big Bang, something happens in these dense pockets. The first stars ignite. They're not like our sun. They're behemoths, hundreds of times more massive. They burn ferociously and die young in supernova. These first lights end the cosmic dark ages. They also begin to pollute the pristine gas. They forge the first heavy elements: carbon, oxygen, iron, the building blocks for future planets and life. Over the next few 100 million years, these first stars gather into small, chaotic protogalaxies. They merge, drawn together by gravity. It's a bottom-up construction. Small structures build larger ones. By the time the universe is 1 billion years old, the first true galaxies are taking shape, great disks and ellipticals. Their shapes influenced by the mergers that built them and the spin of the dark matter halos they live in. Now accelerate the clock further. Billions of years pass. Galaxies aren't islands, they're social creatures. They gather into groups, then clusters, then superclusters. They stream along the dark matter filaments of the cosmic web. Drawn toward the densest intersections, where they meet, they sometimes collide. Slow, majestic dances that can span hundreds of millions of years. They trigger new bursts of star formation. They reshape structures. Our own Milky Way bears the scars of such mergers in its halo of ancient stars. By the time the universe reaches its current age, 13.8 billion years, the web is fully realized. A sponge-like structure of brilliant filaments and immense, dark voids. The timeline shows something. The construction wasn't fast. It wasn't explosive. It was a slow, relentless accumulation. A gentle gravitational tug, acting on a whisper of a difference, compounded over cosmic epochs. What began as a quantum suggestion became, over eons, a galactic command. Each step was simple. Gravity pulls, matter gathers, but the cumulative effect across billions of years is the complexity we see when we look deep into the sky. We're living in the long, slow echo of that first instant. The cosmic web is defined by its emptiness as much as by its light. For every bright filament of galaxies, there's a void. A huge spherical region of almost nothing, and these voids aren't accidents. They're the other half of the quantum blueprint. overdensities grew into galaxy clusters. But the underdensities, the valleys in that early landscape, they became something else. Gravity pulled matter toward the hills. It drained the valleys. Over billions of years, those regions emptied out. What was left were these immense bubbles, some hundreds of millions of light years across, with just a few lonely galaxies inside. So a void isn't just empty space, it's an architectural element, a negative imprint of how it all began, a fossil of absence, and studying them gives you different information. Galaxy clusters are complex, they're messy. Gravity, gas physics, stellar feedback, it all interacts. The pure signal of the initial conditions gets lost in that later chaos. But a void is simpler, it's quiet, the physics there is cleaner, dominated by the gentle tug of dark energy and the traces of the universe's expansion. That makes the size and shape of voids incredibly sensitive probes. They hold a complementary record, mapping their distribution, how many large ones versus small ones, how spherical or stretched they are. Cosmologists can test the same primordial power spectrum from a new angle. They can measure the effects of dark energy with real precision. Think of the cosmic web like a stretching rubber sheet. The voids are the parts being pulled taut. How fast they expand, their growth over time, that tells us about the repulsive force of dark energy, the force that dominates now. So when you look at a map of the large-scale structure, you shouldn't just see the bright knots. You have to see the dark spheres. They're not just a backdrop, they're active participants, sculpted by the same quantum whispers that built the galaxies. Their profound emptiness is a direct consequence of that first moment of imbalance. In the grand narrative, the voids tell the story of what was lost, what flowed away to create everything we see shining. The cosmic web isn't static, it moves, it changes. For most of the universe's life, gravity was in charge. It built everything, but then something else showed up, dark energy. It doesn't build things, it pushes them apart. It's a repulsion built into space. For ages, gravity was stronger. It pulled matter into those filaments and clusters, starting from those tiny quantum seeds, but the universe kept expanding. The matter thinned out, gravity's grip got weaker, and dark energy, the energy of empty space, stayed the same. Its push became more powerful compared to gravity's fading pull. About 5 billion years ago, things tipped. Dark energy became the main thing in the universe. The expansion, which had been slowing down since the beginning, started to speed up. That changed the future of structure. It's like trying to grow a garden in soil that's turning to sand. The seeds are there, they could grow, but the ground itself won't support it. That's dark energy's effect. On the biggest scales, the accelerating expansion makes it hard for gravity to pull things together across the huge voids. It stretches spacetime, it pushes galaxy clusters farther apart. The formation of new superclusters from those thinning filaments is basically stopping. The universe is getting lonelier. That big construction project that started with a quantum whisper is now ending. The scaffold is built, but the builder is leaving. This creates a tension in how we see things. We have the starting point, the quantum blueprint that made the pattern, and we have dark energy's late influence, which controls how that pattern changes going forward. To understand the whole story, you need both. The subtle details of galaxy clusters today, the exact sizes of the voids, they hold the mark of both the beginning and this late force. By measuring how structure has grown over the last few billion years, we can weigh dark energy's effects. We can see its repulsive hand in how the cosmic web's growth has slowed. It's like watching a film of the universe being built, but the last part is playing in reverse, in slow motion. The first push from quantum fluctuations created the potential. The long, patient pull of gravity turned that potential into galaxies, and now the gentle, steady push of dark energy is deciding the final shape. It will set the ultimate fate of the cosmic web. leaving it frozen, isolated, stretched thin across an expanding void. The seeds were planted in a fiery instant of quantum chance, but the harvest will happen in the cold, quiet eternity of dark energy. Our universe's story feels like it had to happen this way. But it didn't. That original design could have been different. The quantum fluctuations that started everything, they had a specific strength, a specific pattern. If those had been just a little off, the cosmos would be something we wouldn't recognize. If the amplitude of those fluctuations was larger, much larger, the early universe would have been all peaks and valleys. Those dense regions wouldn't be gentle hills, they'd be mountains, matter mountains. Gravity's pull there would have been overwhelming from the very beginning. So instead of gas slowly gathering into the first galaxies, matter would have just collapsed catastrophically. It could have formed huge black holes almost immediately, swallowing any chance for stars or galaxies before they could even start. The cosmic web would be a web of singularities, just a dark tapestry of gravity pits. But if the fluctuations were weaker, much weaker, then the opposite. The density variations would have been whispers, too faint for gravity to get a grip, especially with the universe expanding so fast. Everything would have stayed incredibly smooth, a near-perfect fog of hydrogen and helium just expanding. No dark matter halos could take hold, no gas could cool and condense. The cosmos would be vast, dark, and barren, forever uniform, forever simple. No stars, no galaxies, no web, just an endless, quiet expansion into darkness. Our reality is in a narrow window between those two extremes. The fluctuations were strong enough for gravity to do its work, slow, patient work, but not so strong that everything just collapsed into chaos right away. It's a Goldilocks condition, finely tuned, it seems, for complex structure to gradually emerge. It allowed for that hierarchical buildup, small halos merging into bigger ones, galaxies forming, clusters gathering, over billions of years. That balance points to a link, a deep one. The parameters of quantum physics in that first instant, the rules for the inflattened field, they seem connected to the possibility of a cosmos that can build itself. A cosmos that can be more than a smooth soup or a graveyard of black holes. A cosmos that can, over immense time, give rise to the conditions for stars and planets. And maybe life. The fact we're here to think about this connection, that might be the most remarkable part. It suggests our universe's quantum beginning wasn't just any random roll. It was a roll that allowed for a story that could be told. These ideas can get tangled in the way people talk about them. You hear it said that quantum fluctuations are something from nothing. It's a powerful image, but in physics it can be misleading. The quantum vacuum isn't a philosophical void. It's not nothingness. It's a sea of pre-existing fields humming with latent energy. And the fluctuations are ripples in that sea. They're temporary borrowings from the universe's own energy budget, governed by the strict accounting of quantum mechanics. So it's not creation from a true philosophical nothing. It's the dynamic activity of a something that's fundamental to reality. Then there's the phrase, inflation is just a theory. In everyday language, a theory can mean a guess, but in science, a theory is the highest level of explanation. It's a framework that ties together a vast web of evidence. Inflation is a theoretical framework, yes, but it makes specific, testable predictions. The near-scale invariance of the fluctuations, the flat geometry of the universe, the specific pattern of hot and cold spots in the cosmic microwave background. These aren't guesses, they're predictions that have been confirmed by observation after observation. To call it just a theory misunderstands the weight of the evidence behind it. And then we sometimes say these quantum fluctuations created galaxies. That's a poetic shorthand, but the actual mechanism is more subtle, and in many ways more beautiful. The fluctuations didn't reach out and mold gas clouds into spirals. They didn't directly cause anything. What they did was provide the slightest of nudges. Barely their difference in the density of the early cosmos. That was the seed. Gravity did the rest. Over billions of years, gravity acted on that initial condition, amplifying it through a slow, relentless feedback loop. The quantum fluctuation provided the whisper. Gravity turned it into a shout. So the galaxies aren't built by quantum mechanics in a direct way. They're built by gravity, following a map that was drawn by quantum mechanics. This distinction matters because it shows how the universe works. It connects different realms of physics. The quantum world sets the initial conditions. The classical world of gravity executes the plan. It's a partnership across scales. Clarifying this isn't about nitpicking language. It's about honoring the true, nuanced story. A story where the universe's grandest structures aren't magically conjured, but emerge through a lawful, step-by-step process. A process that began with the faintest signature of uncertainty in the fabric of spacetime. This conversation between scales, it shows something about nature, the story of cosmic structure starting from quantum whispers. That's not a lonely story. It's part of a family of stories told across the universe, the physics of a tiny fluctuation growing into a vast pattern. That's a universal plot. You see it in places that have nothing to do with galaxies. Take a pot of water heating on a stove. At first, the surface is calm, smooth, but as heat rises from below, that uniform state becomes unstable. The tiniest convection current, a microscopic swirl of warmer water, can start to rise, and if conditions are right, that tiny swirl doesn't fade, it gets amplified. It organizes the fluid around it. Suddenly, the whole surface breaks into a pattern, a beautiful hexagonal pattern of rolling cells. That's Rayleigh-Bénard convection. A vast, orderly structure coming out of molecular chaos, guided by a simple instability. The math that describes it has a familiar shape. It describes a uniform state, a small perturbation, and a feedback loop that magnifies that perturbation into a dominant pattern. It's the same narrative arc as the cosmic story, just with water and heat instead of dark matter and gravity. Or look at a tiger's stripes, a leopard's spots. For decades, biologists wondered how such precise patterns could form from a uniform embryo. The answer came from a mathematical model, proposed by Alan Turing, the father of computer science. He showed how two simple chemicals, an activator and an inhibitor diffusing through tissue at different rates, could spontaneously generate patterns from randomness. A tiny, random variation in chemical concentration gets locked in, amplified, creating alternating stripes or spots. Again, it's the physics of instability and pattern formation. The same fundamental principles that decided where a supercluster would form also decide where a dark stripe appears on a tiger's back. The scales are unimaginably different. Billions of light years versus a few centimeters, but the underlying mathematical language is strikingly similar. This creates a dialogue across science. Cosmologists studying the grandest patterns can share insights with condensed matter physicists studying crystal formation, or with biologists modeling cell spread. The challenge of understanding how order emerges from disorder, that's a common frontier. Sometimes a technique developed to analyze galaxy clustering finds a new use predicting how a material's fracture lines spread. A model created to simulate the early universe might be adapted to understand crowd movement or how a forest fire spreads. These are all complex systems where small initial differences lead to large-scale, organized outcomes. This universality, it's reassuring. It suggests the process that built our cosmic home isn't a bizarre, one-off event. It's an expression of a deeper, more pervasive principle. Nature has a toolkit for building complexity, and she uses it everywhere, from a boiling pot to the patterning of a shell, from the branching of a river delta to the majestic architecture of the cosmic web. We see the same story repeated, a story of chance providing the seed and simple, relentless laws providing the growth. It means by looking up at the galaxies, we're also learning a fundamental grammar. The grammar of how things come to be, and that knowledge born in the cosmos echoes all the way back down to our world. The fine-tuning this narrow window raises a difficult question. Why are the quantum fluctuations just right for us? One answer from physics and philosophy is the anthropic principle. It's a simple idea, but a controversial one. In its basic form, it says the universe we see has to be compatible with observers. We can't find ourselves in a cosmos that couldn't produce us. So the fact that the quantum seeds had the precise amplitude for galaxies and stars and planets, that's not a lucky accident we need to explain. It's a necessary condition for us to be here to notice it. If the fluctuations had been different, there would be no one to ask why. This isn't a traditional scientific explanation. It doesn't tell us how the fluctuations got their specific properties from the laws of physics. It's more like a selection effect. Imagine you're a fish born in a pond. You might marvel at how perfectly the water suits your gills. It's temperature just right for your biology, but of course it is. You couldn't be born in a pond of molten rock or in the vacuum of space. You can only find yourself in an environment that allows you to exist. The anthropic principle applies that logic to the entire universe. We can only measure the cosmic constants and the primordial fluctuations from within a universe that permitted our evolution. For some, this feels like a cop-out, a way to avoid searching for a deeper, more fundamental reason. A truly predictive theory of everything, they argue, should uniquely determine all the constants, including the strength of those initial quantum whispers. The anthropic principle, by contrast, seems to accept a multitude of possibilities. It finds its strongest footing with the multiverse. If there are countless bubble universes, each with randomly different physical laws and initial conditions, then it's no surprise we find ourselves in one of the rare bubbles where the numbers lined up to make complex life possible. In that vast cosmic landscape, our universe isn't special by design. It's special by selection. Even as a controversial interpretation, the principle adds a layer of self-reference to our story. It connects the quantum code of the early universe to the possibility of consciousness. The faint patterns in the cosmic microwave background aren't just a map of galactic destiny. They are, in a real sense, a prerequisite for the mapmakers. The same quantum jitter that seeded the Virgo supercluster also made the eventual emergence of astronomers inevitable. This intertwines our quest for understanding with the very conditions that allowed it to begin. We are not just passive observers of a cosmic drama. We are an active, if late arriving, part of its logical conclusion. Our curiosity about the cosmos is itself a product of the cosmos's specific initial conditions. This realization doesn't provide easy answers, but it reframes the entire search. It reminds us that in asking where we came from, we are also exploring why we are here to ask at all. The story we have is powerful, but it's incomplete. We've traced a line from quantum whispers all the way to galactic superclusters, yet the beginning of that line vanishes. It goes into a place where our physics breaks down. The inflattened field, that mysterious thing that drove the explosive growth of space, it's still a profound question mark. We know what it did. We can describe its effects with beautiful precision. But we don't know what it is. Is it a fundamental particle, something waiting to be discovered in some future experiment we can't even imagine? Or is it an emergent property? A symptom of something even more basic, a deeper layer of reality we haven't glimpsed yet. Its fundamental nature is the ghost in the machine, the ghost in our entire cosmic narrative. And that leads to a more dizzying question, one that presses against the very idea of a beginning. Did inflation itself have a start? Our equations describe a process. They take a pre-existing speck of spacetime and stretch it. But what created that speck? What was the initial condition? Was there a timeless state, a quantum foam of fluctuating geometries where our bubble of inflation just spontaneously emerged? Or does the idea of a beginning itself dissolve? In the domain of quantum gravity, time might become a statistical property, not a fundamental stage. We're peering into a conceptual abyss where our language of cause and effect may no longer apply. That domain is the Planck epoch, the first 10 to the negative 43 seconds. A time when the universe was so small, so energetic, that gravity has to be described quantum mechanically. Here are two great pillars of physics: quantum mechanics and general relativity. They refuse to speak to each other. They produce nonsense answers. This is the frontier, quantum gravity, and within it lies the true origin of everything. Did spacetime itself crystallize from a more fundamental substrate? Were the quantum fluctuations that seeded our cosmos, were they themselves born from the quantum jitter of geometry? Our current story of inflation is a magnificent chapter. But it might be chapter 2. Chapter 1 is still unwritten, waiting for a theory that can unite the very large and the very small. So our search for answers turns back to the data. Looking for clues we might have missed. Could the pattern of fluctuations in the cosmic microwave background hold subtle imprints, not just of inflation, but of an era that came before it? It's like finding fossilized footprints in rock that is itself ancient. Astronomers scour the maps for statistical anomalies, unexpected correlations, strange asymmetries, things that might be relics of a pre-inflationary universe. The cold spot, the large-scale alignments, these could be mere statistical flukes. Or they could be the first faint whispers from a time before time, etched into the quantum blueprint by processes we don't yet understand. This is where the journey leads now. The path from quantum fluctuations to cosmic web gave us a framework, a coherent story that explains an astonishing amount of what we see. But in doing that, it illuminated the vast darkness just beyond its edges. Every answer has refined the questions, made them sharper, deeper, more fundamental. These aren't failures, they're invitations. They guide the next generation of telescopes, the next ambitious simulations, the next leap in theoretical insight. The universe began with a mystery encoded in its fabric, and our pursuit of that mystery is now its own unfolding story. A story of curiosity reaching back toward its own source. The quantum blueprint of the universe, that's not just for labs, it's a story in the data. And that data is open. The Sloan Digital Sky Survey, those archives, they're public. You can pull up images, millions of galaxies, each one a point of light, tracing the filaments of the cosmic web. This isn't a simulation. These are the real, observed positions, the final, luminous outcome of those ancient quantum seeds. With a few clicks, you navigate this three-dimensional atlas. You fly through the same vast voids and clusters the cosmologists study. It makes the abstract tangible. You're not just hearing about the large-scale structure. You're seeing it with your own eyes, built from the collective light of billions of stars. That public access, it transforms cosmology from a distant science into a personal exploration. It invites you to witness the architecture firsthand, to grasp the sheer scale of the pattern that began as a microscopic whisper, and your curiosity can go further than just looking. You can actually contribute to the mapping. Projects like Galaxies Zoo, they harness human perception, something computers still struggle with. Scientists were overwhelmed. Millions of galaxy images from automated surveys. They needed help classifying them. Is this galaxy a spiral or an elliptical? Is it merging with another? So they asked the public, hundreds of thousands of volunteers, students, retirees. They logged on. They spent minutes here and there, looking at stunning images of distant islands of stars, clicking to describe what they saw. This collective effort, this citizen science, it's been monumental. Volunteers have classified galaxies, Those classifications led to the discovery of entirely new types of objects. They've helped trace the subtle distortions, the distortions caused by dark matter. Every classification is a data point, and millions of these data points help refine our maps. Maps of the cosmic web, they help astronomers understand how galaxies of different shapes and sizes populate the dark matter scaffolding. Each click by a volunteer is a small act. An act of cosmic cartography, helping to fill in the details of the grand design. This connection is profound. When you help classify a galaxy on your screen, you are participating in a chain of discovery. A chain that stretches back to the first instant of time. That galaxy exists because of a specific quantum fluctuation, stretched by inflation, grown by gravity over billions of years. Your act of observation and categorization, it's the latest step, a step in a 14 billion year process. It democratizes the quest for understanding. You don't need a PhD or a telescope, you just need curiosity and an internet connection. You become part of a global community, working together to read the universe's story. This personal link bridges an impossible gap. It connects the quiet moment of your discovery at a computer to the violent quantum birth of everything. It means the story of the cosmos isn't locked away in journals. It's a living narrative, and we are all invited to help write its next pages, simply by looking up. By wondering and by adding our own small piece to the map of all that is. That journey is almost impossible to hold in your mind. The numbers are too vast. The timescale's too immense, but think of a single quantum fluctuation, a tiny, random event. Its scale is a billion times smaller than an atom. It lasts for an instant so brief it has no name. It is, for all purposes, nothing, and yet, that nothing was stretched across the entire sky by a force of expansion so violent it defies analogy. It was frozen into the geometry of the universe. It became a subtle hill in the density of everything. Then, for nearly 14 billion years, gravity took over. The gentle, unyielding force of gravity, it pulled patiently on that hill, drawing specks of dust, then gas clouds, then stars, then galaxies toward it. Over epochs longer than all of human history, that microscopic seed grew. It gathered a city of stars, then a metropolis of galaxies. It became part of a filament in the cosmic web. A thread of light millions of light years long. The connection here isn't just a link, it's a continuous thread, an unbroken chain, from the probabilistic fuzz of the quantum vacuum to the slow-motion dance of galaxy clusters. There is no seam, no moment where one set of laws hands off to another. It is one single, coherent story, a story written in the language of physics, but told across a canvas of unimaginable scale. This is one of the most profound realizations science has given us. The universe is not a collection of separate realms. The very large and the very small are not just connected. They are two expressions of the same underlying reality. The rules that govern the spin of an electron also, indirectly, govern the spin of a galaxy. The uncertainty that defines a particle's position also defines the position of our galactic home. When we look through a telescope at the Andromeda galaxy, that faint smudge of light, we are also, in a real sense, looking at a quantum event. An event that happened in the first trillionth of a second of time. We are seeing its echo amplified across the ages. This continuity does something to our sense of place. It shrinks the feeling of cosmic loneliness. We are not isolated beings on a tiny rock, looking out at a cold, indifferent universe of separate things. We are embedded in a process that began with the fundamental fabric of reality and unfolded, step by lawful step, to produce the ground we stand on and the stars we wonder at. Our curiosity, our drive to understand, is not an outside observer peering in. It is the universe itself in our form, beginning to comprehend its own origins. We are the universe's way of tracing that thread back to its source, of reading its own story, and in that reading we find not just answers but a deeper kind of awe. An awe built on connection, not just on scale. The chain is complete. From a quantum whisper to a cosmic command, we followed a thread of cause and effect across the entire history of everything. Linking the smallest events to the largest structures we can see, it's one of the most elegant stories science has to tell. It shows a universe that isn't a collection of separate parts. It's a single, unified process, the same physics that describes a virtual particle flickering in a vacuum. That same physics describes the slow gravitational dance of the Virgo supercluster. There's no break between these realms, just a continuous unfolding of consequences across 14 billion years. This unity is a powerful reminder. Our cosmic home, with all its splendor and mystery, didn't appear by magic. It didn't appear by arbitrary design. It emerged through the lawful, step-by-step operation of fundamental principles. Quantum mechanics provided the initial, random seed. Inflation provided the explosive magnification. Gravity provided the patient, relentless builder. And dark matter provided the invisible scaffold. Each piece fits together, tested against the hard evidence of the sky, the cosmic microwave background. The three-dimensional map of galaxies, the intricate computer simulations that recreate it all. The story isn't finished. Every new telescope, every deeper survey refines the narrative. It asks sharper questions about the inflattened field, about the nature of dark matter, about the first instant before inflation began. Our understanding is a living thing. It grows as we peer further back, as we look closer at the details. This journey of discovery is itself a human echo of the cosmic process, a small beginning of curiosity, amplified by collaboration and technology into a vast and growing body of knowledge.